The major objective, the measure of central tendency or averages, is to reduce the huge mass of data into single figures. The contents of the measures of central tendency are the arithmetic mean, median, mode, use of mean, median and mode, and merits and demerits of mean, median and mode. Measures of central tendency or averages reduce the huge data into single figures. These single figures represent the entire distribution. There are certain requirements of a good average. Arithmetic mean, median and mode are the most commonly used averages. Each has got its advantages and disadvantages. Arithmetic mean satisfies almost all the characteristics of a good average. Therefore, it is the best average. But in particular cases, median and mode are suitable. Arithmetic mean is defined as the sum of the values of a group of items divided by the number of items. Weighted arithmetic mean is better than simple arithmetic mean in certain cases, whereas different importance should be given to different items in the series, as in the case of computation of index numbers. Median is a positional average. It is the value of the middle item of a series when it is arranged either in ascending or in descending order of magnitude. It is the value of n by 2th item in case of continuous series, or n plus 1 divided by the second item in the case of discrete series, where n stands for the number of items. Interpolation formula is adopted in the case of continuous series. Median divides the series into two equal parts, one part having values greater than the median and the other less than it. Likewise, quartiles, octiles, deciles, etc. divide the series into 4, 8 and 10 equal parts respectively. These are called as partition values. Mode is also a positional average. It is the value of the item which has got the greatest frequency density in its immediate neighborhood. Interpolation formula is adopted to find out mode in case of continuous series. Mode is affected by frequencies of preceding and succeeding groups. In case of bimodal and multimodal series, grouping and analysis table are necessary. Scales of measurement and measures of central tendency. If we have data on some characteristics of students and we wish to describe the group, we would be trying to look for an appropriate measure of central tendency. It would be pertinent to note that selection of appropriate measure of central tendency would largely depend upon the nature of data, more specifically the scale of measurement used for representing it. Several kinds of averages may be worked out. Here we will discuss the mode, median and mean for data collected on nominal, ordinal and interval scales respectively. Now let us look at the arithmetic mean. The arithmetic mean or arithmetic average is one of the most common measures of central tendency and is defined as the sum of the values in the data group divided by the number of values. In statistics, a descriptive measure of a population or a population parameter is typically represented by the Greek letter, whereas a descriptive measure of a sample or a sample statistics is represented by Roman letter. Thus, the arithmetic mean for a population of values is represented by the symbol mu, while the arithmetic mean for a sample of values is represented by x bar. The formulas for the sample mean and population mean are x bar, that is the mean for samples. The formula is sigma x by small n. Mu is equal to sigma x by capital N, or the number of cases. Operationally, the two formulas are identical. In both cases, one sums all of the values and then divides by the number of values. However, the distinction in the denominators is that in statistical analysis, the lowercase n indicates the number of items in the sample, while the uppercase n typically indicates the number of items in the population. Now, let us see what is a geometric mean. The geometric mean of n values is determined by multiplying all lowercase n values together, then taking the nth root of the product. It is useful in taking averages of ratios. The geometric mean is often used for data which take only on positive values and the values can vary significantly, that is by orders of magnitude. An example of such data in biomedical applications is the concentration of various substances in blood and other body fluids. Let us now calculate mean for ungrouped data. When raw data are given, the mean is computed by adding all the individual values and dividing by the total number. Let us look at an example. Let us compute mean for the scores given below. The scores are 25, 36, 18, 29, 30, 41, 49, 26, 16 and 27. Mean is calculated by sigma x by n, that is sum up all the individual values and divide it by n, that is the size is 10. 297 divided by 10, the mean is 29.7. Let us calculate the mean for group data. There can be two situations of group data. 1. When scores and frequencies are given. 2. When data have been grouped, that is frequency is given for each class interval. In the second case, we may compute either by long method or by the short method using the assumed mean. These are explained. Let us calculate the mean for the following data. Just calculated the formula mean is equal to sigma fx by n, where x is the individual score, f is the frequency and n is sigma f, that is total number of cases of frequencies. So, by substituting the values in the formula, the mean for the scores is 35.4. Take an example for the second situation, that is calculating mean for group data with class intervals. Look at this data. The first column, the class intervals are given. The second column, mid values are taken. Third column, the frequencies are given. And the fourth column, the deviation from the assumed mean is calculated. And finally, FD is calculated. So, substituting these values in the formula, we would calculate the mean. Mean is equal to assumed mean plus sigma FD divided by n into C. C is the class interval. So, the values would be like this: 45 plus within brackets minus 180 into 10 divided by 180, and the mean for this distribution is 35. Now, let us discuss about the merits and demerits of mean. Merits. It is rigidly defined, it is easy to understand and easy to calculate. It is based upon all the observations. Of all the averages, arithmetic mean is affected least by fluctuations of sampling. This property is sometimes described by saying that the arithmetic mean is a stable average. With regard to demerits, it cannot be determined by inspection, nor it can be located graphically. Arithmetic mean cannot be used when we are dealing with qualitative characteristics which cannot be measured quantitatively, such as intelligence, honesty, beauty, etc. Arithmetic mean cannot be obtained if a single observation is missing or lost or is illegible unless we drop it out and compute the arithmetic mean of the remaining values. The relationship between the mean and median. The characteristics of mean, median and mode have been discussed in the preceding sections, besides mentioning some situations where they can be appropriately used. Mean, median and mode differ from each other on various counts. These should be used as per the nature of the data indicated by the scale of measurement used and the purpose in hand. However, the mean is a more precise, reliable and stable measure. Its use should be avoided when data are skewed or truncated. If some decision is to be taken on the face value of data, mode is the best measure. But to have a suitable measure when data are incomplete or skewed, median may be preferred. If further statistical analysis is to be carried out, we should go for mean. It will not be desirable to consider any one of them to be superior or inferior in all situations, as it is rather contextual. We should consult an expert if required. For any symmetrical distribution, the mean, median and mode all coincide in value. For a positively skewed distribution, the mean is always larger than the median. For a negatively skewed distribution, the mean is always smaller than median. As compared with mean, mode is affected to a great extent by fluctuations of sampling. With regard to its uses, we first consider the use of these measures of average for representing population data. The value of the mode indicates where most of the observed values are located. It can be useful as a descriptive measure for a population group, but only if there is one clear mode. On the other hand, the median is always an excellent measure by which to represent the typical level of observed values in a population. This is true regardless of whether there is more than one mode or whether the population distribution is skewed or asymmetrical. The lack of symmetry is no special problem because the median wage rate, for example, is always the wage rate of the middle person when the wage rates are listed in order of magnitude. The arithmetic mean is also an excellent representative value for a population, but only if the population is fairly symmetrical. For non-symmetrical data, the extreme values will serve to distort the value of the mean as a representative value. Thus, the median is generally the best measure of data location for describing population data. The mode is not a good measure of location with respect to sample data because its value can vary greatly from sample to sample. The median is better than the mode because its value is more stable from sample to sample. However, the value of the mean is the most stable of the measures. The wage rates of all 650 hourly employees in a manufacturing firm has been compiled. The best representative measure of the typical wage rate is the median because a population is involved and the median is relatively unaffected by any lack of symmetry in the wage rates. In fact, such data as wage rates and salary are likely to be positively skewed with relatively few wage or salary amounts being exceptionally high and in the right tail of the distribution. Next, we will move on to median. When data have been arranged in rank order, the measure of central tendency may be found by locating a point that divides the whole distribution into two equal halves. Thus, median may be defined as the point on the scale of measurement below and above which lie exactly 50% of the cases. Median can therefore be found for truncated data provided we know the total number of cases and their possible placements on the scale. It may be noted that median is defined as a point and not as a score or any particular measurement. Now let's discuss about finding median in ungrouped data. For finding out median in ungrouped data, let us study the following example. In the example given, let's find the median for the scores 2, 5, 9, 8, 17, 12 and 14. Here we have 7 scores. On arranging them in ascending or descending order, we may have the sequence of scores as 2, 5, 8, 9, 12, 14 and 17. We find that there are 3 cases above and below 9, and 9 itself is the midpoint of unit interval 8.5 to 9.5. Thus, 9 divides the whole distribution into 2 equal halves. Therefore, 9 would be the median in this case. Another example, let's find the median for the scores 12, 17, 18, 15, 20 and 19. The first step towards finding the median would be to arrange the given scores serially in ascending or descending order. You will get 12, 15, 17, 18, 19 and 20. Of the 6 scores here, 2 scores are below 17 and 2 above 18. The scores 17 and 18 fall in the middle of the distribution. Here we are not in a position to define median unless we divide this interval covering both the middle scores into 2 equal halves. The midpoint of the interval 16.5 to 18.5 would be 17.5. Now let's see how median can be calculated for a group data. As stated earlier, median is a point on the scale of measurement below which exactly 50% cases fall. Obviously, 50% cases will be above it. For calculating the median, the assumption made in the case of group data is that frequencies are evenly distributed within the class interval. Let's take an example to illustrate this point. Find the median for the distribution. In the above example, there are a total of 40 cases. We have to find a point below and above which lie 20 cases. There are 13 cases in top 3 class intervals and 19 cases in the bottom 4 class intervals. The points segregating the values into 2 halves may be found in class interval 30 to 34, which has 8 cases in it. It is thus called the median class. Assuming that these 8 frequencies are evenly distributed within the class interval 30 to 34, we may find the median point, which has to be 1 case about 29.5. There are 8 cases covering a space of 5 units. Hence, the median would be calculated by using this formula. Median is equal to L plus N by 2 minus FB divided by Fm into I, where L is the lower limit of median class, N is the total number of cases, Fb is the cumulative frequency below the median class, Fm is the frequency in median class, and I is the size of class interval. Using this formula for the previous example, you can see that median is calculated as 29.5 plus 20 minus 19 divided by 8 into 5. That is 29.5 plus 5 divided by 8. It is 29.5 plus 0.625, and the median for the example is 30.13. Now let's look at the merits and demerits of the median. Merits. It is rigidly defined. It is easily understood and is easy to calculate. In some cases, it can be located merely by inspection. It can be calculated for distributions with open-ended classes. With regard to demerits, in case of even number of observations, median cannot be determined exactly. We merely estimate it by taking the mean of two middle terms. It is not amenable to algebraic treatment as compared to mean. It is affected much by fluctuations of sampling. Mode. Mode is the value that occurs most frequently in a set of values. Such a distribution is described as being unimodal. For a small data set in which no measured values are repeated, there is no mode. When two non-adjoining values are about equal in having maximum frequencies associated with them, the distribution is described as being bimodal. Distributions of measurements with several modes are referred to as being multimodal. Data obtained on the nominal scale is of a classificatory type and mostly qualitative. We can count on the number of cases in each category and obtain the frequencies. We may then be interested in noting down the class which is most populous or popular. We frequently deal with scores in measurement and education. The score obtained by the largest number of individuals is the mode of that group of scores. For example, if in a section of 40 students of class 9, the number of students obtaining the score of 55 is the highest. 55 would be called the mode of the scores for that section. Generally, such values are seen to be centrally located with other values in either direction having relatively lower frequencies. Thus, the mode presents a rough estimate of the most typical or the average score in a group of values. It is not essential to have precise scores of all the individuals of the group for finding out the mode. For continuous variables, mode provides a quick measure which is less precise and less dependable as compared to other measures of central tendency. If you draw a frequency polygon or a histogram, you will notice the maximum height of this point or the bar. Sometimes the scores of a group tend to concentrate on two distinctly separate places on the scale. In such a situation, the distribution is said to be bimodal, and the value or score with highest frequency cannot be said to be the mode. You may examine the following histogram and frequency polygon. You may notice that the distribution has two peaks, one at score 6 and the other at score 14. Obviously, 14 cannot be the only mode here. Hence, it represents a bimodal distribution having two modes at 6 and 14. Some distributions can even be multimodal, that is, having more than two modes. We may define mode as the point on the scale of measurement with largest frequency in relation to other values in the neighborhood. Let's now find mode for an ungrouped data. In a simple ungrouped set of measures, the mode is a single measure or score which occurs most frequently. For example, if the scores of 10 students are 13, 12, 14, 15, 12, 14, 1, 12, 14 and 14, the most frequent score is 14 as it has been obtained by 4 students, which is the mode for the given ungrouped data. Now let's have a look at the mode for the grouped data. When the data have been grouped in terms of class intervals and frequencies, the point of greatest concentration of frequencies or the peak in the frequency distribution happens to be the mode. In such a situation, the mode can be identified by inspection alone. The mode is the midpoint of the class interval having the greatest frequency. Because of this estimation, it is sometimes referred to as crude mode. Let's have a look at the example. In the given distribution, there are maximum, that is 8 frequencies in the class interval 90 to 94. So, the midpoint is, that is 92 is the mode. You may come across some distributions where more than one mode could be observable. In the above distribution, the highest and near highest frequencies are at two distinct points, that is, in class intervals 80 to 89, the frequency is 12, and the class interval 40 to 49, frequency is 15. So, it will have two midpoints of the respective class intervals, which are 84.5 and 44.5. Mode is usually interpreted as simple inspectional average to roughly indicate the center of concentration in the distribution. Let's discuss the merits and demerits of mode. Merits: mode is readily comprehensible and easy to calculate. Like median, mode can be located in some cases merely by inspection. Mode is not at all affected by extreme values. Mode can be conveniently located even if the frequency distribution has class intervals of unequal magnitude. Demerits: mode is ill-defined. It is not always possible to find a clearly defined mode. It is not based upon all the observations.